Every advanced chip in production today, the kind powering the servers, the handsets, the base stations that run modern networks, gets its first defining moment not from a laser or a silicon wafer, but from a liquid poured in quantities measured in liters across a spinning disk the width of a dinner plate. One bottle, roughly a day of production on a single coating machine. And that bottle, for every leading-edge chip that exists, was compounded in Japan. The bottle is ArF Immersion Photoresist. I am going to follow it backward, from the coating machine in the fab all the way to the sealed cleanroom where it was formulated. And at each node, I am going to mark whether China has a route around it, or whether the line simply ends. That is the question this map is built to answer. A technological breakthrough is not a faster chip or a bolder announcement. It is a change in the shape of a dependency map. A new line drawn around a node that used to be a dead end. What I am tracing here is not which photoresist produces the sharpest feature. It is which nodes on this particular map have bypasses and which ones do not. Those are different questions, and confusing them is the most common analytical mistake I see in coverage of this supply chain. We start at the far end of the chain, the coater track inside the fab, which is where the bottle gets opened. A spin coating mechanism deposits the resist across the wafer surface in a film that can be thinner than 100 nanometers. The thickness has to be uniform to within a fraction of a nanometer across the entire disk. Before a single pattern is printed, before the scanner fires, that film has to be perfect. And nothing about that requirement is forgiving. If the bottle does not arrive, the coater does not run, and there is no buffer chemical that substitutes. Chinese domestic production of high-end ArF immersion resist has been reported by Chinese industry sources, and some analyst estimates to sit at roughly 10% self-sufficiency for leading-edge requirements as of 2024, with a stated industry target approaching 40% by 2026. I want to be clear about what those numbers are. They are directional signals from reported targets and partial estimates, not independently confirmed volume benchmarks. What is confirmed is that the bulk of the ArF immersion resist consumed in Chinese leading-edge fabs still arrives in bottles compounded in Japan. A missed shipment does not slow a line. It stops it. Here is where I want to push back on a framing I see consistently. Chinese domestic resist producers are sometimes described as simply behind, as if the gap is one of speed on a shared track. That is not the honest read. Some Chinese producers are genuinely competitive at 28 nanometer nodes and above. The accurate picture is that there are now two separate maps. One for legacy process nodes, where Chinese domestic supply is becoming real and confirmed, and one for the leading edge, where the Japanese chemical houses still hold every junction. Conflating those two maps is the analytical error that produces the most misleading headlines about this supply chain. Node reached, the fab coater, first point of resist consumption. Status, a choke point with a bypass under construction. Chinese domestic supply is real at older process nodes and growing, but at the leading edge, the line still runs almost entirely through Japanese suppliers, and a disruption at that source stalls production with no confirmed substitute at scale. From the coater, the line runs back one step, not to a shipping container, not to a port, but to a recipe. A ArF immersion photoresist is not a commodity chemical you mix from widely traded stock. It is an engineered polymer system in which a base resin is designed to change its solubility when struck by deep ultraviolet light at 193 nanometers. Inside the bottle, alongside that resin, is a photoacid generator, the molecule that actually catches the light pulse and triggers the chemical change that makes patterning possible. Then come inhibitors, surfactants, and solvents that are tuned, specifically tuned, to the optical and thermal parameters of the scanner the resist will run on. Change the scanner, and the formulation has to change with it. The formulation is the node. And when I follow the line to this node, it runs directly through two Japanese companies. Shin-Etsu Chemical and Tokyo Ohka Kogyo are reported by industry analysts to hold together roughly 80% of the global high-end ArF and extreme ultraviolet resist market. No independent analysis I have found disputes the direction of that figure, though the exact split between the two companies is not public information. In 2023, Japan brought Photoresist among the semiconductor materials placed under export licensing controls, a list reported to cover dozens of firms across categories that touch advanced lithography. The mechanism is important. This is not an outright ban. It requires review. But the practical effect is that the chemistry itself, not just the finished product, but the formulation know-how that produces it, is now a controlled node. Think of the older cities built where geography forced every road in a district to converge at the one point where a river could be crossed. You can build more roads on either bank. You can widen the approaches. But if there is only one crossing, every vehicle passes through it. Shin-Etsu's position in high-end resist is that crossing. The roads on either side have been getting busier for years. The crossing is still the crossing. This is the point I find most consistently underweighted in the conversation about semiconductor export controls. The control on extreme ultraviolet lithography machines from the Dutch equipment maker gets told constantly, because the machine is a physical object the size of a truck that you either have or you do not. The export control on a formulation recipe is harder to see. You might have the chemicals. You might even have a bottle that looks correct. But if the polymer architecture inside it is not tuned to the scanner's illumination profile, the wafer print's wrong, and you may not immediately know why. The wall is not a locked door. It is a set of instructions written in a language that took decades to develop, and the absence of that language is not always visible until production goes wrong. Node reached. The ArF immersion resist formulation, held predominantly by Shin-Etsu Chemical and Tokyo Ohka Kogyo, now under Japanese export licensing. Status: a choke point the line cannot reach yet. Chinese producers have demonstrated resist at less advanced nodes, but the molecule-level architecture for leading-edge ArF immersion, and especially for extreme ultraviolet, has not been independently confirmed in Chinese domestic production at volume. Behind the formulation is another layer, the raw chemical inputs the recipe is built from. Following the line here, I find a split. The bottle's contents require specific upstream building blocks, the acrylic monomers that form the base polymer, and the photoacid generators that are the reactive core of the system. These are not the same tier of complexity. Reports from Chinese chemical industry publications and some foreign analyst commentary suggest that domestic Chinese producers have made measurable progress on several commodity and near-commodity monomer types used in photoresist. Those are real gains, and I do not want to minimize them. But the photoacid generator class is a different situation. These molecules require precise synthetic chemistry and purity levels that are significantly harder to achieve, and a portion of the most sensitive photoacid generator types are still reported to be sourced from Japanese and European chemical suppliers. I am flagging this as territory where confirmed volume data is not available to me. I am treating the monomer progress as directional and real. I am treating the photoacid generator import dependency as reported and partially confirmed, not fully benchmarked. A junction box in an electrical grid is not a glamorous piece of infrastructure. It is simply the point where several incoming lines get sorted and routed forward. Take it out, and the wire you have on both sides of it is just wire going nowhere. Upstream chemistry is the junction box behind the formulation node. Some of those incoming lines now have domestic Chinese wire running through them. Some still terminate at a foreign post. Here is my hypothesis, and I am still testing it. The photoacid generator subsegment is where I would watch for the next move, not the finished resist, and not the extreme ultraviolet formulation. It is narrow enough, and the synthetic chemistry is specialized enough that a single well-capitalized domestic producer reaching confirmed volume there would not generate the same geopolitical signal as a new fab coming online. If that line closes domestically, the bypass story in the upstream chemistry segment becomes meaningfully more credible than most current assessments suggest. The move, if it comes, will probably be quiet. Node reached. Upstream resist chemistry. Monomers and photoacid generators. Status: a choke point with a bypass under construction. The commodity monomer tier appears to be increasingly domesticated based on available reports, while the most sensitive photoacid generator types remain partially or largely foreign-sourced, with no confirmed domestic volume at leading-edge specification. 3 nodes traced. The map so far is not a simple wall. It is a gradient, a partial bypass at the coater level, a harder wall at the formulation. An uneven picture in the upstream chemistry where some lines have been rerouted and others have not. But there is one node I have been holding back, the one that sits at the far end of all of this and has no bypass at all. ArF Immersion. Resist and extreme ultraviolet resist are not the same product. The distinction matters more than most general coverage of this supply chain acknowledges. Extreme ultraviolet lithography operates at 13.5 nanometers, a wavelength so short that the light cannot pass through air and must travel through a vacuum. The resist chemistry running in that environment requires fundamentally different architecture, higher sensitivity to a much weaker light source, far stricter control over line edge roughness, and the ability to function in a process environment without the water immersion layer that ArF lithography uses as a lens extension. The base polymer, the photoacid generator chemistry, the inhibitor balance, all of it has to be redesigned from the ground up. The development timeline for extreme ultraviolet resist has been measured not in years, but in decades of iterative feedback between resist chemistry teams and scanner development teams. No Chinese domestic producer has been independently confirmed producing extreme ultraviolet resist at volume for leading-edge nodes. The formulation knowledge is concentrated in Japanese houses, Shin-Etsu, Tokyo Ohka Kogyo, and JSR among them, that have been iterating on extreme ultraviolet chemistry in close collaboration with the scanner manufacturer and leading foundries for years. The reinforcing structure here matters. You cannot optimize a resist formulation for a scanner you do not have access to run at volume. The absence of the machine closes the feedback loop the chemistry depends on, which means that even if access to the machine arrived, the resist would not be ready. 2 choke points that each make the other harder to bypass. The strongest argument for a future route around this node is not a domestic chemical breakthrough in the near term. It is architectural. Extreme ultraviolet lithography is not the only path to advanced patterning. Multi-patterning with ArF immersion resist can extend certain node geometries further than the mainstream industry roadmap emphasizes. If Chinese fabs pursue that path aggressively and successfully, the urgency of the extreme ultraviolet resist wall decreases, not because the wall falls, but because the road around it gets longer and more capable over time. Some analysts also note that resist chemistry development could theoretically decouple from scanner access if simulation and electron beam testing infrastructure are available, though that path would be substantially slower. Both sides of that argument are structurally honest. This is a genuine dead end today, with no confirmed bypass. It is also a node whose strategic centrality depends on which patterning path the Chinese semiconductor industry decides to commit to. That is not a tension I can resolve from current evidence. I can only hold both reads and note that the choice being made in the next several years inside Chinese fab planning will determine which one matters more. The map is now complete enough to read in full. The near end of this network has genuinely changed. Legacy ArF resist at older process nodes is increasingly supplied domestically inside China, and that is a real shift from where the map stood 5 years ago. The commodity monomer tier in upstream chemistry is partially domesticated based on available reports. Those are not token gains. For the fabs running at 28 nanometer nodes and above, the dependency has meaningfully reduced. But the gradient hardens at exactly the point where process technology is most critical. The leading-edge ArF immersion formulation remains predominantly Japanese and is now under export licensing. The most sensitive photoacid generator chemistries have no confirmed domestic volume at specification. The extreme ultraviolet formulation has no confirmed Chinese domestic supply at all. My reading stated plainly, this network does not close into self-sufficiency at the leading edge on any timeline I can trace from the evidence currently available. At the legacy tier, it may already be closer to self-contained than the headline coverage suggests. Those are two different maps, and the distinction between them is not closing. It may be widening as the leading edge advances, and the gap between legacy chemistry and frontier chemistry grows larger. That sealed bottle I followed from the beginning, the one the coater track consumes in roughly a day of production, is still being compounded in Japan for every chip that matters at the frontier. The route to it runs through formulation knowledge that was built over decades, through upstream chemistry that is partially but not fully domesticated, and through an extreme ultraviolet variant that has no bypass yet. The bottle started as a concrete object, and it ends as a map. The shape of the network is clearer now than it was before I opened it. The junction that controls the light controls the pattern. The junction that controls the pattern controls the chip. And the junction that controls the chip is still, for now, a bottle compounded in a Japanese cleanroom. The photoacid generator tier is the node I am watching most closely. If a Chinese domestic producer reaches confirmed volume there within the next 2 years, the shape of this map changes in ways that export controls on finished resist may not fully offset. Which node do you think moves first? And does it matter if the extreme ultraviolet wall holds while the lines behind it shift? Drop your read in the comments, and if you want to follow the next line on this map as it moves, subscribe. The next trace picks up where this one ends.